Welcome back to the lecture, and let us look at the other example too.
And by the way, one can get an ML estimate for the for any parameter of any distribution. For instance, let us say that we assume we want an ML estimate for the variance of a Gaussian distribution, we can do the same thing. So now the derivative will become with respect to matrices, same algebra, yeah, covariance matrix. Or you can, let us say that you assume your underlying density to be, let us say, an exponential distribution, then it is a single parameter model. So you can estimate, get an ML estimate for that as well, right. So this is a technique which is general enough. All you have to do is compute the log likelihood, take the derivative of that with respect to the parameter under consideration, and get the estimate. That is it. Okay. I will give you another example for the case of a general discrete random variable, and then we will move on. Discrete random variable or a general discrete random variable. Okay, the previous case, what can be a practical example of the previous case? Practical example of previous case is, let us go back to that same X-ray example, right. You can model the class conditional density actually as a Gaussian density in some 500 dimensions. If your image is of 200 by 200, then you are talking about estimating the mean of a Gaussian density in 4, no, 200 into 200 is 4 followed by 4 zeros, which is 40,000 dimensional space, correct. That is how you can look into it, and that is continuous. The distribution of pixels of an image is Gaussian. You have made an assumption that it is Gaussian in that particular space, and you estimate the underlying density function. Does it make sense, right? So now let us take the example of a general discrete random variable where D is V1, V2, we have Vn. This is sampled IID from PV, where every Vi, so please observe this Vi can take A1, A2 up to Am with probabilities P1, P2 up P1, P2 up to Pm. So this is the general case of any discrete random variable. See, every discrete random variable can be modeled like this. So what am I saying? Let us say that you have a case of data where you are dealing with a discrete random variable that can take m discrete values with probabilities P1 to Pm. What is an example? Coin toss. Coin toss can take, it is a Bernoulli random variable, right, to take one of two values with probabilities P and 1 minus P. The other example is roll of a die. It can take value 6 separate values with probabilities P1 to P6 and so on. You see, right. So any discrete random variable that can take 1 out of m values with probabilities P1 through Pm can be modeled like this. Now what are the parameters that we estimate here? They are P1, this is the parameter, this is our theta vector. There are m thetas that we want to estimate here. I count from 1. Oh yeah, that's, yeah, it's not, yeah, that's correct, m minus 1, because it's a good point, it will come out in a while. So when you solve this optimization problem, we will look into this, because you cannot solve this problem, optimization problem, in an unconstrained way. Why? Because of the precise reason you said, they sum to 1. Good point, yeah, good observation. Okay, is that clear? So this technique can be used to model any discrete density, right, any discrete random variable. Okay, so let us look at how to do this. Now what do we have to do? We will have to find, okay, so let us first say that the parameters theta is this particular set. How do we start the ML estimation? We start by making a distributional assumption on the underlying density p theta. For a discrete random variable, what p theta do you assume? Come again? Why binomial? See, binomial is not, this is not binomial. Why is this not binomial? Binomial is multiple independent trials of a Bernoulli random variable is binomial. This is not a Bernoulli random variable. This is a random variable that can take m values. Yeah, some people, it's not even multinomial. People call it multinolly. Just extension of Bernoulli is what is called as multinolly. It's just general discrete random variable. So we'll have to write the density function for this. How do we write the density function for this? See, a Bernoulli random variable is a general, is a special case of this. Okay, but if you extend the idea of Bernoulli random variable to m outcomes or m possible discrete values, how do you write the density function is the question. It's non-trivial. So we need this this idea called one hot representation. Okay, let us look at that. So let's do what is to express the density function of this. For this random variable, we need one hot representation.
So would it be mass function?
It will be mass function. Yeah. Mass function can also be called a density function, not the other way around. Okay. Anyway, so it is to the mass function for this random variable. We need what is called as a one hot representation. What is that? Now for each, okay, let me write that. So one hot representation. This is just for the algebraic convenience. Okay. So what we write is. So for each Vi, define an auxiliary random variable Zi as follows. Zi is equal to Ci1, Ci2 up to Zim, where all Zi's they are all either 0 or 1, and Zij is equal to 1 for j such that Vi is equal to Aj, 0 otherwise. I mean, it's pretty simple written in a complicated form. So let me just explain what it is, then we'll go to the math. See, the data that we have, what is the kind of data that we have here? The data is V1, V2 up to Vn, right? If it's a discrete random variable that we are considering, all of the Vi's, okay, will take one of these A values, isn't it? Suppose we are looking at rolling of a die, then the data that we will have will look like 3, 2, 4, 1, 6, 7 and not 7, only 6 faces, 3, 2, 4, 1, whatever, right? You understand? So every discrete random variable, every realization of this discrete random variable can belong to one of the m possible values that we have. Make sense? And that's the data. Now what I am doing is to every data point, which is a single value that the discrete random variable take, I am actually constructing an m dimensional 0, 1 vector. What is m here? M is the number of discrete values that the random variable can take. How am I constructing that that particular vector is that this vector will contain 0 in all places, okay, except for in that position which the Vi random variable realized into. Does it make sense? So let me give you an example. So example is, suppose D was like this, which is we are looking at a roll of a die. we have 2, 3, 4, 1, 6 and so on, right. And here my Vi can take values 1, 2, 3, 4, 5 and 6, right. This is how the data would look like, correct. Now for every Vi I have a Zi, right. So Zi, so Z1 will define Z1 to be 0, 1, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, correct. And Z2 is 0, 0, 1, 0, 0, 0 and so on. You got it, right. This is called the one hot representation. Does it make sense? See, I just transform my data which had a single value like this 2, 3, 4, 5 like that from there to a 6 or m dimensional one hot vector. This is called one hot because of obvious reasons. Only one of the positions is hot, the other are cold. Right? That's why it's called the one hot representation. Do you get it? See, now look at the math. So for every Vi we define an auxiliary random variable Zi which is defined as this. Zi is equal to Zi1 to Zim. All Zi's will take value between one of the two values 0 and 1 such that Zij is 1 for only that j for which this Vi is Aj and 0 otherwise. Make sense? Had I only written on the abstract form and not given an example, it would have been difficult to understand, is it? Okay, I mean that is a very subjective opinion, right? So anyway, you got it. So now what happens is my data, so new data will be D equal to, we have Z1, Z2 up to Zn, right? So each Zi is is a discrete vector of length m. See, if I write, you get this notation, right? I am saying that it is a discrete vector which will only take values 0 and 1 and there are m of them. Okay, this is the new data that we deal with. I mean, what is the fun of rewriting this data this way? You remember we did it because we had to write the underlying density mass function. Okay, now will this representation make the mass function writable? Turns out it can be written. What is now p theta of Zi is equal to P1 times, okay, actually write it as p theta of Vi because that is what we need. P1 times Zi1 into P2 times Zi2 into, so this is all product into Pm times Zim. Why is this the case? See, what are these Zij's? They are the elements of capital Zi corresponding to Vi, correct? And which one of this will be 1 for Vi? It will be that particular entry which the Vi correspond to, right? Now, suppose Vi has taken the fourth value, then P1 to the power of 0, P2 to the power of 0, P3 to the power of 0, P4 to the power of 1, and so what will remain? Only P4 will remain. So the density, let us write it this way, no? So Vi is equal to the jth value, or what is the value that we said? It was Aj, no? Hold on. P theta such that Vi is equal to Aj is this. Now Zi for this particular thing will look like, it is all zeros and 1 in one position and 0 everywhere, correct? It is an m length vector and this will be the jth position. Get it? So therefore P theta of Vi equal to Aj will be Pj, and that is what we need. Did you get it? Right. So without this you cannot write the underlying mass function this way. So you want that auxiliary random variable to be defined. You understand why this was defined now. So P theta of Vi is given by the product of j equal to 1 through m P j to the power of C I j. Does it make sense now? That is it. We wanted to write our density function this way, otherwise you cannot differentiate it, and that is why we defined that auxiliary random variable. That is it. Yeah. So P theta of Vi equal to Aj, what is this equal to, by the way? This is equal to Pj. If Vi takes the value Aj, then this is equal to Pj, because that is how we have defined it. Yeah. So if I now say that Pj does not correspond to poor joke, that itself becomes a poor joke. That is the irony. Yeah. Okay. Are you okay now? So what we should do now? This is our density function. Now we have to estimate the parameters, and remember that our theta, the parameter vector that we are trying to estimate is P1, P through P2 up to Pm. No, it takes m values. Right. So how do we do this? So we get our theta star to be the one that maximizes the log likelihood, which is equal to arg max theta. We have, there is also this 1 by n, no, log of, what is P theta? P theta is the product, correct? The rest is algebra. So we have arg max 1 over n I is 1 to n, and there is, use the law of logarithms. Okay, this is what it's going to be. Now we have to differentiate this, right? We have to differentiate this with respect to, see, this does not look like a function of theta at all. Remember that theta is nothing but P1 to Pj, right? Otherwise if you differentiate this thing with respect to theta, when there is no theta, it will go to 0, right? So this Pj is what our theta is, remember that. So we will have to differentiate this. Can we differentiate this and put to 0? So okay, so let me write it explicitly. You differentiate this with respect to Pj. Now tell me what Pj maximizes this. See, if we have to look at this function, okay, and Zi can only take values 1 and 0, okay, which is non-negative, and Pj, because they are probabilities, they are also between 0 and 1. Now there is no negative number here, and the function that we are considering is monotonic, which is log. So if you were to maximize this function with respect to Pj, what value of Pj would, no, I have not said that Pj is bounded now yet. If I don't bound Pj and then solve this optimization problem, because this is unbounded, the value that maximizes this function is Pj that takes infinite value. We don't want that to happen because we know that Pj is a probability. So what should we do? We should add constraints to the optimization problem, right? So adding constraints to the above optimization problem, I put constraints to the optimization problem, what will happen? What constraint should we add? We will have to say that ensure that my Pj's are bounded between 0 and 1. Is this enough? Not. We will have to say that if you add all Pj's over all possible values, it should add to 1. Okay. Now how do you solve a constraint optimization problem? So the new problem is L, the new objective function. So arg max maximize L theta subject to it's bounded and it adds to 1. So how do we solve a constraint optimization problem? Construct the Lagrangian and make it an unconstrained problem and differentiate it. I mean, differentiate the Lagrangian. So write down the Lagrangian, which is what was our objective function? So it was 1 over n I 1 through n log, was another summation. Yeah, summation over n and summation over j summation over I and j Zij log Pj plus lambda times 1 through m Pj minus 1 plus alpha times Pj minus 1 plus some other beta times minus Pj. Why did I write all these? 3 constraints, right? One is that the sum has to be 1, which is the first Lagrangian. The other has to be that, yeah, it has to be less than 1. The other is that it should be greater than 0. That's it. I wrote 3 Lagrangians here. Now you differentiate this entire thing with respect to Pj and put it to 0. I will completely skip the algebra. Will you please take it as an exercise and do it? Please complete the algebra. So how do you solve a constraint optimization problem? Differentiate this with respect to the objective function first, and then with respect to Lagrangians, and find out what the Lagrangians are, and take the optimal Lagrangians and put it back to the objective function and get the final objective, final optimizer. All of you know this, right? So, you have done a course on optimization. This is simple 101, right? Optimization 101. I will skip the algebra. So, finally, after solving, even today's ML building happens like this. So, the real juice lies in formulating the problem. Optimization is done using computers. Throw it to GPUs, it will solve gradient descent for you, but constructing the optimization, in fact, engineering actually lies in translating the real world problem into a math problem, right, and formulating it as a problem that can be designated and solved through computers. Now a new type of engineering will be emerging. See, somebody was asking me the other day that there is AI now, GPTs and all that can answer any question that you ask. So why do you need human beings, right? My answer to that is, yeah, I mean, or why do you need teachers or anybody? GPT answers questions, but who will tell you what questions to ask? You can actually relate it to yesteryear's calculators. See, calculators can solve math problems, but somebody has to give it an instruction as to what is an important problem to solve. I think that is where the actual value lies from now on. Understanding solving which problem creates value in society is where the actual skill lies. Once you do that, there are powerful machines that you can designate your work onto, which would solve problems for you, but the question is what problem is to be solved. Okay, so now that we have formulated the problem, it can be very easily solved using the standard algebra. If you do that, what do you expect Pj to be, the estimate of Pj to be, the ML estimate of Pj to be? To our surprise, it will be, I am just trying which notation did I use for this. It is actually this, it will be the number of times Aj has occurred in D divided by n. So what in my notation, what is that? It is Zij summation over, this is summation over 1 through n, we have Zij, is this correct? Divided by n, this is what it is. Please do this, please do the algebra, it will come out that way, right? I mean, you can see this actually here, there is Zij here, you differentiate and put it to 0, it will come that way, right? So that's it. So now we knew this all the time, that if you are given a discrete random variable and you need to tell me what is the probability that this discrete random variable takes a particular value j, then what do? We just see how many times this j has appeared and divide that by n. That is the maximum likelihood estimate. What you are actually doing is assuming that the underlying density has this form and writing down the K divergence and minimizing the K divergence, and this is the estimate that you get. Okay. By the way, one question can come up here. This is still an estimate, right? How do we know whether this estimate is close to the true parameter value? So, this question is similar to the question of how close is the minimizer of the empirical risk to the minimizer of true risk, and there are metrics that would quantify the goodness of the estimators. Uh, these are called the concentration inequalities and other bounds, which is beyond the scope of this particular subject. There are bounds that would tell you with what confidence can I say that this particular estimator is close to the true value. Just be aware of it, okay. So, I will not go into the deep depth of it. This is the ML estimator for this particular discrete random variable case, okay.
We will stop here and continue in the next lecture.